Tonight, we are going to sit with a question that sounds simple. A question you could ask a child. The question is this: where is everybody? Now let me show you why that question, posed in that specific context, is one of the most unsettling things ever uttered in the history of science. The universe is 13.8 billion years old. Our galaxy alone contains somewhere between 200 billion and 400 billion stars. The observable universe contains an estimated 2 trillion galaxies. The number of stars in the observable universe is roughly 10 times the number of grains of sand on every beach and desert on Earth combined. We are talking about numbers so large that human intuition simply stops working. Your brain can process the words, but it cannot truly picture what they mean. Now here is the thing that matters. Stars are not rare. Planets are not rare. We used to think they might be. For most of human history, we had no idea whether other stars had planets. We could not see them. We had no way to know. The question of whether we were alone in the universe was genuinely open in a way that it almost is not anymore. Because in the last 3 decades, we have discovered something extraordinary. Planets are everywhere. The Kepler Space Telescope, launched in 2009, stared at a small patch of sky containing about 150,000 stars for 4 years. It looked for the tiny dimming that happens when a planet passes in front of a star, and it found planets, thousands of them. So many that astronomers had to revise their estimates of how common planets are. The current best estimate is that virtually every star in the Milky Way has at least one planet. Some have more. Our galaxy alone contains somewhere around 1 trillion planets. 1 trillion planets in one galaxy, out of 2 trillion galaxies. And among those planets, a significant fraction orbit their stars in what astronomers call the habitable zone. The region where liquid water can exist on the surface. Not too hot, not too cold. The Goldilocks zone. Current estimates suggest there are billions of potentially habitable planets in the Milky Way alone. Billions, in one galaxy. And life, as far as we can tell, got started on Earth remarkably quickly. The Earth formed about 4-5 billion years ago. The first evidence of life, simple microbial life, appears in the geological record about 3-8 billion years ago. That means life got started within about 700 million years of the planet forming. In cosmic terms, that is fast. That is almost immediate. That suggests that life, at least simple life, might not be an extraordinarily rare accident. It might be something that happens readily given the right conditions. And here is where you need to think about time, not just space. Time, our sun is about 4-6 billion years old, but the universe is 13.8 billion years old. That means there are stars out there that formed 9 billion years before our sun. Stars that have been burning steadily for 9 billion years longer than ours. If any of those stars have planets in habitable zones, and we have every reason to think many of them do, then life could have gotten started there 9 billion years before life got started on Earth. Think about what 9 billion years means. Humans have had writing for about 5,000 years. We have had agriculture for about 12,000 years. We have been anatomically modern humans for maybe 300,000 years. In 9 billion years, starting from a position similar to where Earth was when life first emerged, what could life become? What could intelligence achieve? What technologies could be developed? What distances could be crossed? Even if we imagine that the development of intelligence is rare, that only a tiny fraction of planets with life ever produce technological civilizations, the sheer number of planets and the sheer depth of time involved should mean that the galaxy is full of civilizations. some ancient beyond our comprehension, some that have been spacefaring for longer than our planet has existed, some that have had billions of years to spread, to build, to communicate, to make their presence known. And yet, we look up at the sky and we see nothing. We listen with our most sensitive radio telescopes and we hear nothing. We search for signs of engineering on a galactic scale and we find nothing. We look for laser pulses, for artificial signals, for the waste heat of giant energy-consuming civilizations, and we find nothing. Nothing, not a whisper, not a shadow, not a single unambiguous signal from anyone else. Where is everybody? This is the Fermi Paradox, named after the physicist Enrico Fermi, who supposedly asked that question over lunch in 1950 while talking with colleagues about the possibility of extraterrestrial life. The legend goes that the conversation had moved on to other topics when Fermi suddenly said, "But where is everybody?" His colleagues apparently knew immediately what he meant, and they had no answer. That was 1950. It is now more than 70 years later. We have built much more powerful telescopes. We have discovered thousands of exoplanets. We have listened to the sky with increasingly sensitive instruments for decades. We have sent our own signals out into the cosmos. We have developed a whole scientific field, the search for extraterrestrial intelligence, dedicated to this question, and we still have no answer. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now make yourself comfortable. Let us begin. Let me start by showing you why the silence is so strange. Because your first instinct might be to say, well, space is big. Maybe they are out there, but they are just too far away for us to detect. And that is a reasonable thing to think. But it does not hold up when you actually sit with the numbers. The Milky Way galaxy is about 100,000 light-years across. That is enormous by any human standard. But here is the thing. Even at speeds far below the speed of light, a civilization could theoretically explore and colonize the entire galaxy within a timeframe that is short compared to the age of the universe. Here is the calculation. Imagine a civilization that develops the ability to travel between stars at, say, 1% of the speed of light. That is far slower than anything like a warp drive. It is slow, patient, but not impossibly slow. At 1% of light speed, crossing the typical distance between neighboring stars, which is a few light years, takes a few hundred years. Not a quick trip. But manageable for a civilization that thinks in long terms. Now suppose this civilization sends out colony ships, and each colony, once established, after a few hundred or 1,000 years, sends out its own colony ships. This is a branching process. It spreads like a wave across the galaxy. And when you run the math, even with these modest assumptions, a civilization could colonize the entire Milky Way within somewhere between 10 million and 100 million years. Probably closer to 10 million if they are motivated. 10 million years sounds like a long time, but the galaxy is 13.8 billion years old. 10 million years is less than 1% of the galaxy's age. If even a single civilization anywhere in the Milky Way had reached our level of technology 9 billion years ago, and had then spent just 10 million years expanding, the entire galaxy should be colonized by now. Every star, every planet, including this one. We should not just be able to detect them from here. They should be here. They should have been here for billions of years. And yet the solar system shows no sign of having been visited. The Earth shows no sign of having been colonized or terraformed by anything other than the life that evolved here. There is no alien infrastructure in our solar system, no megastructures in orbit, no ancient automated probes lurking in the asteroid belt. Nothing. The silence is not just a matter of distance, it is a matter of time. In the time available in the age of the galaxy, the silence should have been broken. Something should be here, and nothing is. In 1961, an astronomer named Frank Drake sat down with a group of colleagues for the first ever scientific meeting on the search for extraterrestrial intelligence. To structure the discussion, he wrote an equation on a blackboard. It was not intended to give a precise answer. It was intended to organize our ignorance, to map out the problem, to show which questions we needed to answer in order to figure out how many communicating civilizations might exist in the galaxy right now. The Drake equation includes the rate at which new stars form in the Milky Way per year. We know this reasonably well. It is about 1 to 3 new stars per year. Then it factors in the fraction of those stars that have planets. When Drake wrote this equation in 1961, this was deeply uncertain. Now we know, thanks to Kepler and other missions, that the answer is close to 1. Nearly every star has planets. Then it asks how many of those planets could potentially support life. Current estimates put this at somewhere between 1 in 10, and every star having at least one potentially habitable world. Then comes the fraction that actually develop life. On Earth, life appeared quickly. Some scientists think this means life is common. Others think Earth might have been extraordinarily lucky. We do not know. Then the fraction with intelligence. Then the fraction that developed detectable technology. And finally, and most critically, how long those civilizations remain detectable. That last term, the lifetime of a civilization, is the most important and most uncertain variable in the entire equation. If civilizations typically destroy themselves within a few hundred years of developing advanced technology, the number of civilizations we could detect right now would be tiny. If they survive for millions or billions of years, the galaxy should be full of voices. When you run the Drake equation with even modestly optimistic assumptions, you get a galaxy that should be full of intelligent life. Thousands of civilizations, millions, and we see none of them. That is the paradox in its full force. There is one idea that, more than any other, captures the eerie logical structure of the Fermi Paradox. An idea that is simultaneously elegant and terrifying. It is called the Great Filter. The Great Filter was articulated by the economist and philosopher Robin Hanson in 1998. The core idea is simple. If the universe is old and big and filled with planets, and if intelligent life has not made itself obvious across the cosmos, then something must be filtering out civilizations. Something is stopping intelligent life from becoming the kind of galaxy-spanning, observable presence that it seemingly should be. There is a filter, and the critical question is whether that filter is behind us or ahead of us. Let me explain what that means. The path from a sterile planet to a spacefaring civilization involves many steps. The emergence of life from chemistry, the development of complex multicellular life, the evolution of intelligence, the development of technology, the survival of a technological civilization past the dangerous period when it has weapons of mass destruction, but before it becomes truly stable. Each of these steps is either easy or hard. Either most planets make it through, or most do not. If most planets fail at one or more of these steps, then intelligent spacefaring life is rare. The filter is the step where almost everyone fails. and the question is where that filter sits. If the filter is behind us, if the hard step is something that has already happened in our evolutionary history, then we have already passed through it. We are the rare ones who made it. The filter might be the origin of life itself, requiring such a specific and unlikely set of circumstances that it has only happened a handful of times in the observable universe. Or it might be the development of complex eukaryotic cells, the kind with a nucleus, which happened only once in Earth's history despite billions of years of bacterial life. Or it might be the development of sexual reproduction, or multicellular life, or any number of other innovations that took billions of years and enormous contingency to achieve on Earth. If the great filter is behind us, the news is actually good. We beat the odds, we are rare, perhaps nearly unique, and the universe ahead of us is open. We can potentially become one of the first spacefaring civilizations in the galaxy, if not the only one. The silence is explained because almost nobody else made it this far. But if the great filter is ahead of us, the news is catastrophic. It means that most civilizations, at some point after reaching our current level of development, fail to survive. Something destroys them. And since we have not yet passed through that filter, we are not yet safe from it. The filter could be self-inflicted, nuclear war, engineered pandemics, runaway artificial intelligence, climate catastrophe, any of the ways that a civilization powerful enough to be dangerous to itself could destroy itself. Or it could be external, some cosmic threat, a gamma-ray burst, an asteroid impact, something that periodically sterilizes technological civilizations regardless of how they choose to behave. If the great filter is ahead of us, then the discovery of life elsewhere in the universe would be the worst news humanity has ever received. Here is why. Suppose we discover simple microbial life on Mars or in the oceans of Europa. At first, this would seem like wonderful news. Life is not unique to Earth. The universe is alive. We are not alone. But think carefully about what this would mean for the great filter. If simple life is common, if microbial life emerges readily on many planets, then the filter is not at the origin of life. That step is easy, which means the filter must be somewhere else. Somewhere further along the path. Maybe the filter is the development of complex multicellular life. Maybe it is intelligence. Maybe it is technological civilization surviving its own power. And if we then discovered the ruins of a dead civilization, the implications would be even more dire. It would mean that the filter is somewhere after intelligence, somewhere very close to where we are right now, or ahead of us. Carl Sagan understood this intuitively. He said that he hoped deeply that Mars was sterile, because if Mars has life, then life is easy. And if life is easy but we still see no advanced civilizations anywhere, then something else must be stopping them. And that something else is probably ahead of us too. The great filter makes the silence meaningful. It is not just an absence. It is a clue, and the clue might be pointing towards something very dark about the future of intelligence in the universe. People have proposed many solutions to the Fermi Paradox over the decades. Some are optimistic, some are deeply unsettling, and a few are so strange that they require an entirely different way of thinking about intelligence and civilization. Let us work through them, starting with the ones that do not require anything terrible to be true. The first and most common optimistic solution is sometimes called the rare earth hypothesis. The idea is that the conditions required for complex life, and especially for intelligent life, are far more demanding than we usually assume. And that Earth is genuinely rare, perhaps nearly unique in meeting all of those conditions simultaneously. Consider what Earth has going for it. It sits in the habitable zone of a stable, long-lived star. It has a large moon that stabilizes its axial tilt, preventing wild swings in climate. It has plate tectonics, which recycle carbon and regulate the long-term climate, and which may be essential for complex life. It has a magnetic field that shields the surface from deadly solar radiation. It has Jupiter, a giant planet in the outer solar system, whose gravity deflects many of the comets and asteroids that would otherwise bombard the inner planets far more frequently. It formed at the right time in galactic history, not too early when heavy elements were scarce, and not in a region of the galaxy where dangerous radiation from nearby supernovae would sterilize the surface. Each of these factors is contingent. Each could have been different. And the rare Earth hypothesis says that when you multiply all these requirements together, the probability of a planet having all of them simultaneously is so small that Earth-like worlds are extraordinarily rare. Maybe only a handful in the entire observable universe. If this is true, then the Fermi Paradox is solved. We see nobody because there is nobody, or nearly nobody. We are the exception, not the rule. The rare Earth hypothesis has its critics. Some of the proposed requirements are disputed. Computer simulations suggest that planets can have relatively stable tilts even without a large moon. The Jupiter shield hypothesis has also been questioned, and some astrobiologists argue that life is far more adaptable than the rare Earth hypothesis assumes, pointing to extremophiles on Earth that thrive in conditions once thought incompatible with life. The debate is not settled. But the rare Earth hypothesis remains one of the most serious and scientifically grounded attempts to explain the silence. A second optimistic solution is that we simply have not been looking long enough or well enough. SETI has been searching for radio signals since the 1960s. That sounds like a long time, but in terms of coverage, we have only scratched the surface. The frequency space is enormous. The timing might be wrong. Maybe extraterrestrial civilizations are not broadcasting continuously. Maybe they only broadcast occasionally. Maybe we happen to be listening at the wrong time. This is sometimes called the cosmic haystack problem. We are looking for a needle in an incomprehensibly large haystack, and we have searched a tiny corner of that haystack so far. The absence of detection does not prove absence. There is genuine merit to this. Modern SETI efforts, especially with instruments like the Meerkat array in South Africa and the planned Square Kilometre array, are dramatically more sensitive and comprehensive than earlier searches. We may simply not have found anything yet because we have not looked carefully enough. A third optimistic possibility is that we are communicating in the wrong way. Maybe advanced civilizations do not use radio waves at all. Radio is a relatively inefficient way to communicate across interstellar distances. Maybe advanced civilizations use lasers. Maybe they use neutrinos, which can pass through matter unimpeded. Maybe they use some form of communication based on physics we have not yet discovered. We would not know what to look for. This is a real challenge for the search. We can only look for things we know how to look for, and the communication methods of a civilization a billion years more advanced than us might be as incomprehensible to us as radio waves would be to a Neanderthal. A fourth optimistic solution involves the nature of advanced civilizations. Maybe after a certain level of development, civilizations no longer need or want to broadcast their presence. They turn inward. They engage with virtual realities so rich and compelling that the physical universe seems irrelevant. They become quiet not because they died, but because they stopped talking. This is sometimes called the transcension hypothesis. The idea is that advanced civilizations do not expand outward into space. They expand inward into the computational richness of miniaturized systems, into virtual environments, into the inner space of mind and consciousness. They become small, dense, and quiet. Not a civilization spreading across the stars, but a civilization living in a grain of competronium, running minds of unimaginable richness on tiny machines that emit almost no detectable radiation. If this is true, the galaxy might be full of ancient, incredibly advanced civilizations that we cannot detect because they are not broadcasting, not expanding, and not doing anything that shows up in our instruments. They have gone dark by choice. Now we get to the solutions that are harder to sit with. The ones that, if true, have implications that reach all the way back to us. The first disturbing possibility is that intelligent civilizations tend to destroy themselves. This is sometimes called the self-annihilation hypothesis, and it has a horrible plausibility. Think about where we are right now as a civilization. We have nuclear weapons capable of ending civilization in hours. We have the ability to engineer pathogens of unprecedented lethality. We are developing artificial intelligence systems whose implications we do not fully understand. We are changing the climate of our planet in ways whose long-term consequences are uncertain. We have accumulated enormous power, and our wisdom, our political systems, our impulse control, our ability to cooperate globally has not kept pace. Every civilization that reaches the technological level we are at faces similar challenges. They all have the equivalent of nuclear weapons. They all have the equivalent of the ability to engineer pandemics. They all face the equivalent of a climate crisis caused by their own energy use. And they all face it at a moment in their development when they are still fractious, still tribal, still motivated by competition and fear as much as by cooperation and wisdom. Maybe most of them fail. Maybe the window between becoming dangerous enough to destroy yourself and becoming wise enough not to is so narrow that most civilizations fall through it. Maybe the great filter is the nuclear age, or the bioengineering age, or the artificial intelligence age, and it is right where we are standing. This is a sobering thought, not because it means we will definitely destroy ourselves, but because it means the silence might be a graveyard. Every star in the sky might orbit a world that once had life, once had intelligence, once had civilizations that looked up at the sky and wondered if they were alone. And then something went wrong. The second disturbing possibility is the zoo hypothesis. Perhaps we are not seeing other civilizations because they are deliberately hiding from us, or more precisely, perhaps they are deliberately preventing us from seeing them. Perhaps there is some form of interstellar community of advanced civilizations that has collectively agreed to leave emerging civilizations alone, to let them develop without interference, and to not reveal their presence until the emerging civilization reaches some threshold of maturity. Like animals in a zoo, we are being observed, protected, but not contacted. This hypothesis has a certain appealing logic. If you imagine a galaxy full of civilizations at different stages of development, the question of how to handle younger civilizations becomes important. Do you contact them? And if so, when? Too early and you might disrupt their development. Maybe the answer that most advanced civilizations have converged on is to wait, to watch, to intervene only to prevent extinction, perhaps, but otherwise to leave the younger species to find their own way. The problem with the zoo hypothesis is that it requires extraordinary coordination. Every civilization in the galaxy would need to agree to the policy and to maintain it perfectly over potentially millions of years. No defectors, no rogue civilizations that decide to make contact anyway, no accidents. The consistency of the silence, if this hypothesis is true, would require a level of coordination that seems almost more unlikely than the silence itself. A variant is the dark forest theory, popularized by the Chinese science fiction author Liu Cixin. The dark forest theory proposes that the universe is silent not because civilizations are rare, but because they are hiding, actively hiding, in fear. The logic goes like this. Every civilization needs resources. Resources are finite. And you can never truly know the intentions of another civilization. Even if they seem friendly today, you cannot be sure they will not become a threat tomorrow. Given this uncertainty, and given that the downside of being wrong, being destroyed by a civilization you trusted, is existential, the rational strategy might be to never reveal your location. And if you detect another civilization, to destroy it before it becomes a threat. In this model, the universe is a dark forest in which every hunter moves silently, because any noise might draw a predator. Civilizations exist, but they have all learned to be silent, and they actively hunt those who are not. If the dark forest theory is correct, then broadcasting our presence with radio signals may have been extraordinarily dangerous. We have been announcing ourselves to a silent, predatory cosmos. Most scientists consider the dark forest theory too pessimistic, requiring assumptions about universal scarcity and universal predatory behavior that may not hold. But it is logically coherent, and it cannot be dismissed simply because we do not want it to be true. Let me step back from theory for a moment and tell you about the actual history of listening, because we have not been entirely silent in our search. There have been moments. Moments that suggested, briefly, tantalizingly, that the silence might not be complete. The most famous of these is the wow signal. On the night of August 15, 1977, a radio telescope at the Big Ear Observatory in Ohio was scanning the sky as part of an ongoing SETI search. The telescope was automated, and nobody was sitting at the controls watching in real time. The data was printed out on paper, and a researcher named Jerry Amen examined it a few days later. What he found in the data was extraordinary. A burst of radio waves at a frequency close to 1420 megahertz, which is the frequency at which neutral hydrogen emits radiation. This frequency is considered special by SETI researchers because hydrogen is the most common element in the universe, and any civilization wanting to communicate across interstellar distances might choose a frequency near this natural beacon. The signal was so strong, so much louder than background noise, so perfectly shaped like what you would expect from a signal coming from a fixed point in the sky, that Amen circled it on the printout and wrote one word in the margin. Wow. The wow signal lasted for 72 seconds, which was exactly how long the telescope's beam took to sweep past a given point in the sky. It fit perfectly what you would expect if you were receiving a transmission from a distant, fixed source. The signal-to-noise ratio was around 30, vastly exceeding the threshold that SETI researchers had set for a signal worth investigating, and it was never heard again. Researchers pointed the telescope back at that patch of sky dozens of times over the following months and years. no repeat, nothing. The wow signal remains, to this day, the strongest candidate for an extraterrestrial signal ever recorded, and it remains completely unexplained. Various mundane explanations have been proposed over the years: Earth-based interference, a satellite, a comet. In 2017, an astronomer proposed that the signal might have come from hydrogen gas around comets that were in that part of the sky at the time. But this explanation has been disputed. The comets in question may not have been close enough to the pointing position of the telescope, and their hydrogen emission should have been too broad and too faint to produce a signal like the wow signal. We simply do not know what it was, and the uncertainty is maddening. The most exciting thing ever detected by SETI, and it happened once in 1977 and was never repeated. There have been other anomalous signals over the years. In 2016, there was enormous excitement about a star called Tabby's star, which was dimming in irregular, asymmetric patterns that did not match anything known to astronomers. Some researchers speculated that the dimming might be caused by a Dyson swarm, a vast array of structures built to capture the star's energy, exactly the kind of megastructure that a highly advanced civilization might construct. The excitement was genuine, but it was ultimately explained by dust, irregular clouds of cometary dust orbiting the star at different distances, causing the complex dimming pattern. The most extraordinary explanation is not usually the correct one, but the very fact that these anomalies are noticed, investigated, and sometimes remain puzzling for years tells you something important. We are paying attention, we are watching carefully, and we are still waiting for something that does not go away. Here is an angle on the Fermi Paradox that most people do not think about. Most of the discussion assumes that intelligence looks like us. That a civilization capable of interstellar communication is something we would recognize as intelligent, that it wants to expand, that it wants to communicate, that it would make itself known in ways we can detect. But what if intelligence comes in forms so alien to us that we would not recognize it even if we encountered it? Think about how we define intelligence. We tend to define it in terms of things humans do: problem solving, language, tool use, foresight, social cooperation, building, communicating. These are the markers of intelligence that we value because they are the markers of intelligence that we have. But there is no reason to think that these are the only possible forms of intelligence in the universe. Imagine a civilization that evolved under radically different conditions. Not on a rocky planet orbiting a star, but in the ocean of a rogue planet drifting between stars, heated by internal radioactivity rather than sunlight, or in the atmosphere of a gas giant, or in some environment we have not imagined. The intelligence that emerges from such conditions might be structured so differently from ours that we might not recognize it as intelligence at all. Or imagine a civilization that has integrated so deeply with computational systems that the distinction between biological and artificial intelligence has dissolved. What does such a mind want? What does it value? Does the concept of interstellar expansion even make sense to it? Does communication with other species interest it? We are assuming that advanced intelligence has goals and desires that we can understand. But a mind 1 billion years more advanced than ours might be as incomprehensible to us as we are to an ant. There is also the question of whether intelligence necessarily leads to the kind of civilization that would be visible across interstellar distances. We tend to assume that a civilization follows a particular trajectory. simple life, complex life, intelligence, language, technology, radio, space travel, interstellar civilization. But this trajectory is based on one data point, us. Maybe it is not universal. Maybe intelligence often evolves in ways that are not oriented toward external communication and expansion. Maybe it turns inward. Maybe it chooses simplicity. Maybe it pursues goals that do not require broadcasting your existence to the cosmos. The Fermi Paradox assumes that advanced civilizations are visible, but maybe they are not. Maybe the most advanced form of intelligence is also the quietest, the smallest, the most hidden. Maybe reaching a certain level of development means becoming effectively invisible to younger, louder civilizations like us. There is a more specific and deeply unsettling subset of the great filter discussion that deserves its own treatment. It involves the possibility that the galaxy is not simply silent, but actively hostile. And the mechanism is not living predators, but something far more ancient and patient. The physicist Freeman Dyson helped articulate the concept of a self-replicating interstellar probe. The idea is straightforward. A civilization wants to explore the galaxy but cannot travel there itself, at least not quickly. So it builds a probe. The probe travels to a nearby star system, uses the resources there to build copies of itself. Those copies travel to the next star systems and build more copies, and so on, exponentially, spreading through the galaxy like a wave. The mathematics of this are striking. A single probe starting from one star system and replicating at each stop could fill the entire galaxy with copies of itself within a few million years. Every star system explored, every planet cataloged, every resource assessed. Now suppose someone built such a probe 1 billion years ago. The galaxy should be full of these probes right now. We should be able to detect them, unless they are deliberately hiding, or unless they have been designed not to make themselves obvious to the species they are observing, watching quietly, gathering data, waiting. This is sometimes called the lurker hypothesis. The idea that self-replicating probes exist in the solar system right now, possibly in the asteroid belt, possibly in the outer solar system, watching and recording but not announcing themselves. We have not made a thorough search for such objects. The asteroid belt alone contains hundreds of millions of objects, and most of them have never been examined closely. Something could be out there, but there is a darker variant. What if the probes are not watchers but destroyers? What if a civilization, perhaps one that encountered an aggressive or dangerous species early in its expansion, decided that the safest approach to other intelligent life was elimination? And what if they built self-replicating probes programmed to destroy any civilization that reaches a certain level of technological development? These hypothetical probes are sometimes called berserkers. In this scenario, the Fermi Paradox would be explained not by the rarity of life, but by the systematic destruction of civilizations once they become detectable. If this is true, then every SETI broadcast we have sent, every powerful radar beam, every radio and television signal that has leaked into space over the past century has been announcing our presence to something that does not want us to be heard. This is a difficult thought to sit with, and I want to be clear that most scientists do not consider the Berserker hypothesis likely. It requires assumptions about the existence and persistence of ancient destructive probes that go well beyond anything we have evidence for, but it is logically consistent. And the absence of evidence is, in this case, exactly what the hypothesis predicts. Let me take you somewhere strange for a moment. Because one of the most discussed solutions to the Fermi paradox in recent years does not involve space or biology at all. It involves the nature of reality itself. The simulation argument, most fully articulated by the philosopher Nick Bostrom in 2003, goes like this. There are three possibilities, and at least one of them must be true. First, virtually all civilizations at our level of development go extinct before reaching the capability to run detailed simulations of minds and universes. Second, virtually all civilizations at the capability level to run such simulations choose not to, for reasons we cannot fully anticipate. Or third, we are almost certainly living in a computer simulation. Here is the logic behind the third option. If any civilization ever reaches the point of being able to run detailed simulations of entire universes, complete with simulated minds that believe themselves to be conscious, then they will almost certainly run many such simulations. Maybe millions, maybe billions. If there are billions of simulated universes and only one real one, then any given observer is statistically far more likely to be in a simulated universe than the real one. Now here is where the Fermi paradox connects. If we are in a simulation, the absence of extraterrestrial life is not a paradox at all. It is simply a design choice. The simulator chose to create a universe with one technological civilization, or with life that does not spread across the cosmos, for whatever reasons motivated the simulation's design. The silence is not evidence of a filter. It is evidence of a setting. Some physicists have taken the simulation hypothesis seriously enough to look for evidence that could distinguish a simulated universe from a real one. If the simulation runs on some kind of discrete computational substrate, there might be a minimum resolution to space and time, a pixelation at very small scales. Some researchers have speculated that evidence for this might be found in the behavior of ultra-high-energy cosmic rays, which should show a particular pattern if space has a discrete grid-like structure. No such evidence has been found, but the absence of evidence is not conclusive. The simulation, if it exists, might be sophisticated enough to conceal its own structure from us. I find the simulation hypothesis interesting less as a literal claim about the nature of reality, and more as a way of illustrating how the Fermi paradox can be dissolved by changing the assumptions about what kind of universe we are in. The paradox assumes a particular kind of universe, one that is real, physical, old, and filled with planets that should have given rise to many civilizations. Change that assumption and the paradox changes with it. There is a deeper subtlety in the Fermi paradox that is easy to miss but important to understand. It involves the question of observer selection, the fact that we are here to ask the question at all. This is sometimes discussed under the heading of the Anthropic Principle. The idea in its most basic form is that we should not be surprised to find ourselves in conditions that permit our existence. By definition, any conscious being asking why the universe is hospitable to its existence is a being that exists in conditions hospitable to that existence. You cannot ask the question if the answer is no. The Anthropic Principle has direct relevance to the Fermi paradox. Suppose the development of intelligence is extraordinarily rare. So rare that in the entire history of the observable universe, it has only happened once, or a handful of times. In that case, there would be no ancient civilizations spreading across the galaxy, no signals, no megastructures, just silence. And the single instance of intelligence that did arise would look around, notice the silence, and wonder why. But there is no paradox here. The silence is simply a reflection of how rare we are. The problem is that we cannot use the anthropic principle to tell us which case we are in. We cannot use it to determine whether the great filter is behind us or ahead of us, whether intelligence is rare because of the difficulty of getting started, or rare because it tends to destroy itself. What the anthropic principle does give us is a way of thinking about probability. If the development of intelligence requires the crossing of many hard steps, and if each hard step is intrinsically unlikely, then the expected time between the first occurrence of intelligence in the galaxy and the second occurrence might be enormous, maybe longer than the age of the universe so far, in which case we are the first. Not because of anything special about us, but simply because the odds required billions of years of cosmic history to produce the first instance, and the second instance has not had time to emerge yet. This is a genuinely possible explanation for the Fermi Paradox. It does not require a great filter that will kill us. It does not require the universe to be hostile or empty or simulated. It just requires that we are early. The first technological civilization in a universe that will eventually be full of them. Pioneers at the beginning of a cosmic era of intelligence. If this is true, the silence is not ominous. It is simply the quiet of a universe that has not yet filled with voices. We are not alone in the deep sense that intelligence is inherent to the universe, but we may be temporally alone, the first to reach this moment, at this time, in this galaxy. And the voices that will eventually join ours are still billions of years from speaking. Let me be concrete for a moment, because it is easy to talk about detection and contact in abstract terms. But what would it actually look like? How would we know if we found something? The most commonly discussed scenario is the detection of an artificial radio signal, a pattern in radio waves that could not be produced by any known natural process. Pulsars, quasars, magnetars all produce radio waves, but they produce them in ways that follow physical laws we understand. An artificial signal would have some signature of deliberate construction, a pattern, a mathematical structure, a prime number sequence, a coded message. The challenge is that distinguishing an artificial signal from a natural phenomenon is genuinely hard. The wow signal looked like exactly what you would expect from an artificial transmission, but it was never repeated. Without repetition, without confirmation, you cannot be certain. If a confirmed signal were ever detected, the procedures are reasonably well established. The detecting observatory would immediately attempt to confirm the signal using a different telescope. If confirmed, they would notify other observatories worldwide. The signal and its location would be shared openly with the scientific community. There would be no immediate response. The international protocols for SETI contact specify that any decision about whether and how to respond should involve the entire international community, not just the detecting institution. What the signal contained would determine a great deal about what followed. A simple repetitive signal might just be a beacon, a way of saying we are here. More complex signals might contain information. Mathematical descriptions of physical constants, diagrams, instructions, or something completely incomprehensible, structured in ways that reflect a totally different mode of cognition. The psychological and social impact of confirmed contact would be, to put it mildly, significant. Every religion would have to grapple with it. every philosophical framework for understanding humanity's place in the universe would need revision. Political systems, institutions, and power structures would be under enormous strain. Some people would be exhilarated, others would be terrified, many would simply not know how to process it. And there is a harder question underneath all of this. What if the signal is not a simple greeting, but a warning? What if the message, once decoded, says something we did not want to hear? Instructions for avoiding some catastrophe, evidence of a threat, a description of what happened to them. These are not idle questions. They are questions we should probably be thinking about more seriously than we currently are. I want to take a step back and be honest about the limits of our understanding. Because in discussing the Fermi Paradox, it is very easy to talk about what we know and to forget how much we do not know. We do not know how common life is. We know it emerged on Earth. We do not know whether that required special circumstances or whether it was essentially inevitable given the chemistry involved. We have not detected life anywhere else. The discovery of biosignatures in planetary atmospheres from telescopes like the James Webb Space Telescope might change this in the coming decades. But right now, our sample size is 1. We do not know how common complex life is. We know that on Earth, simple life persisted for about 2 billion years before complex eukaryotic cells appeared. We do not know whether that transition is typical or extraordinary. The endosymbiotic merger that created the eukaryotic cell might have been extraordinarily unlikely. It might have happened only once in the entire history of life on Earth. If so, complex life might be rare across the galaxy, even if simple life is common. We do not know how common intelligence is. On Earth, intelligence of our type appeared once, in one lineage, after about 8 billion years of life. Other lineages have developed varying degrees of what we call intelligence, but nothing that has led to technology and civilization. This suggests intelligence of the technological kind might not be the inevitable endpoint of complex life. It might be contingent, a historical accident. We do not know how long civilizations typically survive. Our own civilization is perhaps 300 years old in the technological sense, perhaps 12,000 years old in the agricultural sense. We do not know what the future holds. We do not know whether we will survive the next century, let alone the next million years. And we do not know what we are not detecting. Our search methods are limited by our technology, our assumptions, and our imagination. We are looking for what we would recognize. We are listening for what we would broadcast. We may be surrounded by things we cannot perceive because we do not know how to look for them. The honest answer to the Fermi Paradox is this: we do not know why the sky is silent. We have proposed many explanations. Some of them are comforting, some of them are terrifying, none of them are confirmed. The silence is a fact. The meaning of the silence is not yet known. I want to spend some time on something that is rarely discussed in the context of the Fermi Paradox. Not where the other civilizations are, but what the Fermi Paradox means for us, for how we should think about our own future, our own choices, our own responsibilities. If the great filter is ahead of us, then our choices in the next few centuries matter enormously. Not just for us, not just for humanity, but potentially for the trajectory of life and intelligence in the galaxy. If we are genuinely rare, if we are among the first technological civilizations to emerge, then our survival or destruction would represent not just a local tragedy, but a cosmic one, the loss of a rare and precious thing. This gives an unusual weight to questions about existential risk, nuclear weapons, engineered pandemics, artificial intelligence gone wrong, climate change that destabilizes civilization. These are not just important problems for humanity. If we are rare, they are important problems for the galaxy. On the other hand, if the great filter is behind us, if we have already passed the hard steps, then the future is, in principle, open. We are not destined to destroy ourselves. The dangerous phase is something we have already survived in some sense, and the road ahead is longer and more open than we might imagine. This would be reason for profound optimism about the future of intelligence. And if the explanation for the silence is something more neutral, perhaps that civilizations tend to turn inward or become quiet as they advance, then perhaps the future of our own civilization involves a kind of quieting that we cannot currently envision, a maturity, a wisdom, a turning of attention from the outer cosmos to the inner richness of mind. The Fermi Paradox is not just a question about space, it is a mirror. It reflects back at us questions about what intelligence is for, what civilizations do with their power, and whether the story of mind in the universe has a good ending or a tragic one. There is something almost unbearable about the combination of the beauty of the night sky and the silence it contains. 2 trillion galaxies, hundreds of billions of stars per galaxy, trillions of planets, billions of years. And nothing that has definitively announced itself to us. Either we are alone, or something has silenced the cosmos, or something is hiding, or we are simply too early, too young, too limited in our perception to hear voices that are there. None of these answers are comfortable. None of them leave the universe feeling ordinary. The night sky, which most people think of as a backdrop, a decoration, is actually an open question. The biggest question, maybe the only question that matters as much as we think it does. The search for extraterrestrial intelligence is not just an academic exercise. It is the search for the answer to a question that might redefine our understanding of what we are. The tools available to us are improving rapidly. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the largest radio telescope ever built. It will be capable of detecting radio leakage from a civilization at Earth's current level of technological development up to distances of hundreds of light years. For the first time, we will be able to survey a significant fraction of the nearby galaxy with enough sensitivity to detect civilizations that are not intentionally broadcasting, just leaking signals the way we do with our television and radar. The James Webb Space Telescope is already transforming our understanding of exoplanet atmospheres. Future telescopes could potentially detect biosignatures, chemical signs of life, in the atmospheres of Earth-like planets orbiting nearby stars. These would not be signals of intelligence, but they would be signals of life, and finding life, any life, elsewhere would transform the terms of the Fermi Paradox. There are also searches underway that go beyond radio waves. Optical SETI looks for laser pulses that might be used for interstellar communication. Laser pulses can carry enormous amounts of information and can be made extremely focused and directional, making them in some ways more efficient than radio for interstellar communication. If a civilization is trying to send a targeted signal rather than a broadcast, a laser might be the preferred medium. There are proposals to search for Dyson spheres and other megastructures by looking for the infrared radiation they would emit as waste heat. A civilization that wraps a star in a shell of solar panels to capture all of its energy would block visible light, but would radiate all that energy as heat in the infrared. Surveys of nearby stars looking for anomalous infrared excesses are ongoing. There are even proposals to look for signatures of nuclear weapons tests on other worlds, or the atmospheric signatures of industrial civilization, or the spectral fingerprints of manufactured chemicals. All of these searches are speculative, technically challenging, and based on assumptions about what advanced civilizations would do, but they are creative, and creativity is exactly what this search requires. The history of astronomy is full of discoveries made by people who were not looking for what they found. Pulsars were discovered by researchers looking for something else entirely. The cosmic microwave background radiation was found accidentally. Fast radio bursts appeared unexpectedly. The history of the universe reveals itself in ways that confound our expectations. The answer to the Fermi Paradox might come from a direction we have not anticipated, a signal in a frequency we were not prioritizing, an anomaly in an astronomical survey aimed at something completely different, a pattern in data that was sitting unexamined in an archive. The discovery might come tomorrow, or it might take another century, or it might never come because there is nothing to find. We do not know. What we do know is that the question matters, that the silence matters. That the act of listening, of searching, of asking where everybody is one of the most profound things a conscious species can do. I want to end where we began, with the question itself. Where is everybody? We have spent a long time tonight working through the implications of the silence, the great filter. The self-annihilation hypothesis, the zoo hypothesis, the dark forest, the simulation argument, the rare earth, the transcension hypothesis. Each of these is a possible answer to the question. Each of them in its own way is disturbing or comforting or both. But I want to sit with the silence itself for a moment, not as a puzzle to be solved, but as a fact to be experienced. Look up at the night sky on a clear night, far from city lights. What you see beyond the nearer stars and the familiar constellations is the Milky Way, the collective glow of hundreds of billions of stars. And beyond that, invisible to the naked eye but real, utterly real, are 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially orbited by planets, each planet potentially harboring something. Life, mind, voice, and yet silence. The silence is not empty. It is freighted with meaning, with possibility, with fear, with hope. It is the silence before an answer you are not sure you want to hear. The silence of a question so large that the asking of it changes you. Enrico Fermi asked where everybody was over lunch in 1950. He said it almost as a joke, the story goes, and then returned to his meal. But the question did not go away. It has grown. It has deepened. It has attracted the attention of physicists, biologists, philosophers, mathematicians, astronomers, and dreamers of every kind, and it remains unanswered. Maybe there is nobody out there. Maybe we are the first, the only, the exception that proves a rule we do not yet understand. Maybe the universe made life once in this solar system, on this planet, in this moment of cosmic history, and the rest is silence. Maybe there are millions of civilizations out there, all listening, all silent, all waiting for someone else to speak first. A cosmic game of waiting, in which every player is too cautious or too afraid or too wise to announce themselves. Maybe there are signals passing through us right now that we do not know how to receive, messages in a medium we have not discovered. Voices in a language we cannot yet read. Maybe the answer is something none of us have thought of, something that will seem obvious in retrospect, the way so many great discoveries seem obvious once they are made. something that will make us wonder how we could have missed it for so long. The Fermi Paradox is not a problem that has been definitively solved. It is an open wound in our understanding of the universe, a gap between what we expect and what we see. A silence where there should, by any reasonable calculation, be sound. And that silence asks us something, not just about the universe out there, but about us, about what we are, about what we are becoming, about whether we will survive long enough to find the answer. About whether, if we do survive, we will become the kind of civilization that breaks the silence. That sends a signal. That says to the quiet cosmos, we are here, we are thinking, we are listening, and we want to know. The night sky is not empty. It is full of questions. And the most important question of all is the one that a physicist named Fermi asked over lunch more than 70 years ago on a summer day in New Mexico. Where is everybody? We are still listening. Sleep well tonight. The sky is full of stars, and one of them might be listening back. Good night. There is a way of thinking about the Fermi Paradox that cuts through all the philosophy and gets to something almost unbearably precise. It is the mathematics of how rare we might be. Start with the observable universe. It contains roughly 2 trillion galaxies. Each galaxy contains, on average, a few 100 billion stars. That gives us somewhere around 2 times 10 to the 23rd power stars in the observable universe. That is a 2 followed by 23 zeros. More stars than there are grains of sand on every beach of every ocean on Earth, multiplied many times over. Now suppose that the probability of a technological civilization arising on any given planet around any given star is incredibly small. Let us say 1 in a trillion, 1 in 10 to the 12th power. That sounds vanishingly rare. And yet, with 2 times 10 to the 23rd stars, even at those odds, you would expect about 200 billion technological civilizations in the observable universe right now. 200 billion. For us to be alone, not just in the Milky Way, not just in the local group of galaxies, but in the entire observable universe, the probability of a technological civilization arising anywhere would have to be less than about 1 in 10 to the 23rd power. 1 in 100 sextillion. That is a number so small that it is almost meaningless to write it. It is smaller than the probability of randomly selecting the same specific atom twice from all the atoms in the observable universe. It is smaller than almost any probability that arises in physics. For us to be truly alone in the observable universe, something about the development of technological intelligence would have to be almost infinitely improbable. Not just hard, not just unlikely, almost infinitely unlikely. And yet here we are, thinking, wondering, asking the question, either we are that extraordinarily rare exception, or there are others, and if there are others, we should be able to detect them. And the fact that we cannot is the paradox in its most mathematical form. This calculation does not resolve the paradox, but it sharpens it. It shows you that the stakes are not moderate. Either the development of intelligence is almost unimaginably improbable, or the galaxy is full of civilizations that we cannot explain the absence of. There is very little middle ground. The numbers push you toward one extreme or the other. And that extremity, that sense of being forced to choose between 2 alternatives, each of which seems almost impossible, is why the Fermi Paradox is not just a fun puzzle. It is a genuine crisis in our understanding of what the universe is and what our place in it is. There is a particular kind of vertigo that comes from thinking about civilizations that might be ancient beyond comprehension. And I want to sit with that for a moment, because it is rarely considered in full. Our civilization is perhaps 12,000 years old if you count from the beginning of agriculture. It is perhaps 300 years old if you count from the beginning of the Industrial Revolution and the exponential curve of technological development that followed. By any measure, we are extraordinarily young. Cosmically speaking, we have existed for an eye blink. Now consider a civilization that is 1 billion years old. A civilization that arose on a planet orbiting one of the first generation of stars capable of supporting complex chemistry. A star that formed when the universe was perhaps 4 or 5 billion years old. A civilization that has been thinking, building, exploring, and developing for a period of time that dwarfs the entire current age of Earth. What would such a civilization be? What would it want? What would it know? What would it have become? We cannot answer these questions, not meaningfully. The gap between our level of development and a civilization 1 billion years older is likely to be as vast as the gap between us and a bacterium, perhaps vaster. Perhaps the concepts themselves, what a civilization is, what intelligence is, what existence is, would not translate across that gulf. And this is important for the Fermi Paradox. Because when we ask where everybody is, we are implicitly assuming that a very old civilization would be detectable to us, that it would do things we could recognize, that it would broadcast or build or expand in ways that would show up in our instruments. But maybe it would not. Maybe the signature of a truly ancient intelligence is not a Dyson sphere or a radio signal. Maybe it is something we have not thought to look for, or something we cannot look for, or something that is present everywhere but indistinguishable from the background. Some theorists have speculated that the universe itself might be, in some sense, the product of intelligence, not in a theological sense, but in a physical one. If a sufficiently advanced civilization could manipulate the conditions under which universes form, could tune the parameters of new universes, then our universe might carry the fingerprints of its makers. The fine-tuning of physical constants that seems to allow for complexity and life might not be a coincidence. It might be design. This is deeply speculative. There is no scientific evidence for it. But it illustrates how far the thinking about ancient civilizations can go when you follow it honestly. The Fermi Paradox forces us to consider not just the absence of signals, but the entire range of what an ancient intelligence might be and do. And that range extends far beyond what we can currently imagine. Let us think carefully about what it would mean if we actually made contact. Not in the abstract, philosophical sense we have been discussing, but in the concrete, practical, political, and psychological sense. Imagine the scenario. A radio telescope in the Australian outback picks up a signal. The signal is clearly artificial. It repeats. It contains a mathematical structure. Within hours, other observatories around the world have confirmed it. Within days, there is no scientific doubt. Someone somewhere is broadcasting. The location is determined. It is a star system 47 light-years away. The signal is coming from the direction of that star. It is old, of course. It left its source 47 years ago. Whatever sent it, whatever civilization built the transmitter, was there 47 years ago. They may still be there. They may not. Now what? The first question is whether to respond. The international protocols suggest caution. The light travel time alone means that any conversation would take 94 years round trip minimum, but the impulse to respond would be overwhelming. The pressure from governments, from media, from scientists, from ordinary people all over the world would be enormous. What do you say? How do you say it? Who decides? These questions have never been seriously answered. There is no international body with the authority to respond on behalf of Earth. There is no agreed-upon message. There is no consensus on whether we should respond at all, whether announcing our precise location to a civilization 47 light-years away is wise or dangerous. And beneath all the practical questions lies the psychological one. What does it do to a species to know with certainty that it is not alone? That out there, around another star, something intelligent exists. Every tradition, every culture, every religion, every philosophy, every political ideology would be affected. Some would find it vindicating. Some would find it shattering. Some people would feel an expansion of the cosmos, a sudden richness of the universe, a confirmation that mind is not an accident. Others would feel a contraction, a loss of uniqueness, a diminishment of what it means to be human. The history of contact between civilizations here on Earth gives us some warning. When technologically advanced civilizations encounter less advanced ones, the consequences for the less advanced civilization have typically been catastrophic. Disease, displacement, cultural destruction, often genocide. The history of colonialism is a history of what happens when an asymmetry of power meets an asymmetry of culture. We do not know whether the gap between us and any extraterrestrial civilization that has been broadcasting signals would involve a power asymmetry. If they are 47 light-years away and we only just detected their signal, they may not know we exist. They may be broadcasting to the universe in general, not to us specifically. The power dynamic might be more symmetrical than the historical analogies suggest, but we do not know, and the uncertainty is not comfortable. There is a strand of SETI research that argues we should not be broadcasting at all. That we should maintain radio silence, listen carefully, but not announce ourselves. This position is called METI skepticism, where METI stands for Messaging Extraterrestrial Intelligence. Proponents of METI skepticism argue that the dark forest logic, even if it is not fully correct, suggests that some caution is warranted. We do not know what is out there. We do not know how it would respond to our presence. The asymmetry of information, the fact that we would be revealing ourselves to something we know nothing about, should give us pause. Others argue that we have already been broadcasting for decades. Television and radio signals have been leaking into space at the speed of light since the mid-20th century. A sphere of electromagnetic radiation centered on Earth, roughly 80 light-years in radius, contains everything we have ever broadcast. Anyone within that sphere who has the right equipment to listen already knows we are here. The ship has already sailed. Whether that is true in the relevant sense is debated. The signals we leak are diffuse, not directional. They fall off rapidly with distance. Whether they would be detectable at interstellar distances is not clear, but the philosophical point stands. We are not a quiet civilization. We are already making noise. The question of whether to make more, and in what form, is one we have not collectively answered. I want to come back to the moment the paradox was born. Because the story of Fermi and his question is itself worth examining carefully. The summer of 1950, Los Alamos, New Mexico. A group of physicists are walking to lunch. Among them is Enrico Fermi, one of the most brilliant physicists of the 20th century, the man who built the first nuclear reactor and played a central role in the Manhattan Project. The conversation turns, as it sometimes did in those years, to the possibility of extraterrestrial life. There had recently been a cartoon in the New Yorker depicting flying saucers, which were very much in the public consciousness at that time. The Roswell incident had happened 3 years earlier. The possibility of visitors from other worlds was something that ordinary people thought about, that the popular press discussed, and that even serious scientists occasionally addressed. The physicists at the lunch table were discussing, with some lightness, the question of whether alien civilizations might exist. The conversation moved on to other topics, and then Fermi said, suddenly, apparently with no particular context, "But where is everybody?" His colleagues knew immediately what he meant. And they found the question funny, in the way that very deep questions sometimes are funny, because the answer seems like it should be obvious, and yet it is not. They laughed. Fermi did some quick calculations on a napkin, estimates of the number of civilizations that should exist, the distances involved, the travel times, and he concluded that the galaxy should, by any reasonable calculation, be full of life, and yet it was not, as far as anyone could tell. The question was not pursued seriously at that lunch. Fermi did not write a paper about it. He died 4 years later, in 1954, without returning to the paradox that bears his name. It was only in the 1970s that the question began to be treated as a genuine scientific puzzle, when the physicist Michael Hart published a serious analysis of why the galaxy should have been colonized long ago, and why the fact that it had not been was a paradox requiring explanation. But the image of Fermi at that lunch table, eating with colleagues, asking the question almost as an aside, has something important in it, because the question is in some sense obvious. It is the kind of question a curious child might ask, given how big the universe is and how old it is and how common planets are. Where is everybody? Why is it just us? The obviousness of the question is not a mark against it. Some of the most profound questions are the ones that sound almost too simple to need asking. The things that are so obvious they seem beneath investigation until you actually sit with them and realize they are not simple at all. Fermi's question is like that. It sounds simple. It is not. And 70 years after he asked it over lunch in New Mexico, we are still trying to answer it. I want to spend the final chapter of this script on something that might seem unusual for a video about science. I want to talk about how to be comfortable with not knowing. Because the Fermi Paradox, for all its scientific rigor, for all the physics and mathematics and biology it involves, ultimately leaves us in a state of profound uncertainty. We do not know why the sky is silent. We do not know whether we are alone. We do not know whether the great filter is behind us or ahead of us. We do not know whether the silence is empty or full, and we may not know for a very long time. In an age that values certainty, that values answers, that values the definitive statement and the settled question that is uncomfortable. We like to know things. We like to resolve paradoxes. We like the click of understanding when an explanation falls into place. The Fermi Paradox does not give us that click. It gives us deeper questions instead. But there is something valuable in sitting with a question you cannot answer, something clarifying about a mystery that will not resolve. The Fermi Paradox forces a kind of humility that is rare and important. It reminds us that the universe is not obligated to be comprehensible to us, that the questions we can ask may be deeper than the answers we can find, that our instruments and our intelligence and our science, as extraordinary as they are, may be insufficient to resolve the deepest mysteries of our situation, and it forces a confrontation with stakes. Because unlike most scientific puzzles, the Fermi Paradox has personal implications. It asks about our place in the cosmos, about whether we are special or common, about whether the story of mind in the universe is just beginning or nearing its end. These are not just intellectual questions, they are existential ones. They touch something deep in the human need to understand what we are and where we stand. There is a particular kind of awe that comes from staring at the night sky and knowing that the silence you perceive might be full of meaning you cannot read. That somewhere in the darkness between the stars, there might be answers to questions that have haunted our species since we first developed the capacity to ask them. Or there might be nothing. Nothing but stars and emptiness and the accident of our own existence. Both possibilities are staggering. The universe populated with intelligence, ancient and strange and silent, is staggering. The universe with only us, a single bubble of consciousness in an otherwise empty cosmos, is equally staggering. There is no comfortable middle ground. The Fermi Paradox pushes you to the edges, and maybe that is where we need to be, at the edge of what we know, looking out into what we do not. Uncomfortable with the silence, but unwilling to fill it with false certainties, listening carefully, searching patiently, asking the question again and again, even knowing we may not hear an answer, because the question itself is valuable. The asking matters. A species that looks up at the night sky and wonders, that takes the silence seriously, that refuses to stop searching, is a species that is doing something profound with its brief existence in the cosmos. We are conscious matter asking questions of an unconscious universe. We are the universe becoming aware of itself for a moment in this small corner on this small planet under this particular sky. And we are listening. Where is everybody? We do not know. We are still looking. We are still listening. And that is enough for tonight. Sleep well. The stars are out, and the question is still open. Good night. One of the most common responses to the Fermi Paradox is to point at the distances involved. Space is unimaginably vast. The nearest star to our sun is Proxima Centauri, about 24 light-years away. At the speed of our fastest current spacecraft, the Voyager probes, it would take about 70,000 years to reach it. The center of the galaxy is 26,000 light-years away. The nearest large galaxy, Andromeda, is 25 million light-years away. These are distances so enormous that they seem to make interstellar travel effectively impossible, and therefore the absence of visitors seems less paradoxical. But this response, while intuitive, does not hold up under scrutiny, and the reason is time. Yes, interstellar travel at current speeds is impossibly slow, but we have only been a technological species for a few hundred years. We have only been a spacefaring species for about 60 years. Our technology is in its absolute infancy. The history of technological development shows exponential curves. Things that seem impossible in one generation are routine in the next. Things that seem impossible today might be trivial in 1,000 years. Consider nuclear pulse propulsion, a concept developed in the 1950s and 1960s. By detonating a series of nuclear explosions behind a spacecraft, you could theoretically accelerate it to a few percent of the speed of light. At 1% of light speed, you reach Proxima Centauri in about 424 years. At 10% of light speed, you reach it in 42 years. These are not fast by interstellar standards, but they are not forever. Consider the Bussard ramjet, a theoretical spacecraft that would scoop up hydrogen from the interstellar medium and use it as fuel for a fusion engine. If such a device could be built, it could potentially accelerate indefinitely, approaching the speed of light asymptotically, with the additional benefit that relativistic time dilation would make very long journeys feasible from the crew's perspective. Consider antimatter propulsion. If you could produce and store significant quantities of antimatter, the energy density available from matter-antimatter annihilation is the highest of any known reaction. A spacecraft powered by antimatter could potentially reach a significant fraction of the speed of light, making journeys to nearby stars feasible within a human lifetime. None of these are currently practical. The challenges are enormous, but they are not fundamentally impossible. There is nothing in the laws of physics that prevents travel at a significant fraction of the speed of light. The engineering challenges are vast. The energy requirements are staggering, but physics allows it. And crucially, we are asking about civilizations that might be billions of years more advanced than us. The gap between our current technology and the technology of a civilization a billion years older is likely to be greater than the gap between a Neanderthal and a modern engineer. To assume that a civilization a billion years old would be limited by the same constraints we face today is like a Neanderthal assuming that future humans would be unable to cross the ocean because there are no logs large enough to bridge it. If interstellar travel is physically possible, even at a small fraction of the speed of light, then given enough time, a sufficiently motivated civilization could colonize the galaxy. The distances are enormous, but the time available is also enormous, and the paradox stands. Here is a thought that does not come up often in discussions of the Fermi Paradox, but that seems to me important. We have established in modern cosmology that ordinary matter, the kind made of protons and neutrons and electrons, the kind that makes up stars and planets and us, constitutes only about 5% of the total mass energy content of the universe. The rest is dark matter, about 27%, and dark energy, about 68%. Dark matter is something we can detect only through its gravitational effects. It does not emit light. It does not absorb light. It interacts with ordinary matter only through gravity and possibly through the weak nuclear force. It is everywhere. It permeates galaxies. It forms a cosmic web of filaments along which galaxies cluster. It shapes the large-scale structure of the universe, but we do not know what it is. Dark energy is even more mysterious. It is the energy of empty space itself, driving the accelerating expansion of the universe. We know it exists because we can measure the expansion. We know almost nothing else about it. Now here is the thought. What if life or intelligence can exist in forms that do not use ordinary matter? What if there are civilizations built from dark matter? What if there are minds made of something we cannot directly observe, operating on timescales and in environments completely inaccessible to us? This might sound like pure speculation, and it is. We have no evidence for life of any kind that does not use ordinary matter. We do not know whether the physics of dark matter could support anything like the chemical complexity that underlies biology. The coupling of dark matter to itself is almost certainly different from the coupling of ordinary matter to itself, and it is far from clear that the same kinds of structures, polymers, proteins, cells, nervous systems would be possible. But the point is that when we ask where everybody is, we are asking where everybody is that we can see. We are implicitly assuming that technological intelligence would be made of the same stuff we are made of. And that assumption, while reasonable given that it is the only kind of life we know, is still an assumption. If the universe contains forms of intelligence that do not use ordinary matter, they would be completely invisible to us, not just undetected. fundamentally undetectable with any instrument we currently possess or could reasonably conceive of building. The Fermi Paradox would be dissolved not because the civilizations are absent, but because they are made of something we cannot see. Again, this is speculative. There is no evidence for it, but it illustrates how deeply our assumptions about what life and intelligence must be can shape the terms of the paradox. We are searching for ourselves, essentially. We are looking for things that look like us, that use the same physics we use, that build the same kinds of structures we build. Whether the universe contains fundamentally different kinds of intelligence, whether it contains mind that is organized around principles we have not discovered, is a question we cannot currently answer. There is an angle on the Fermi paradox that comes not from astronomy or physics, but from geology and biology. It involves what we are doing to our own planet right now, and what it might suggest about the typical trajectory of technological civilizations. We are living in what geologists call the Anthropocene, the epoch of human influence. For the first time in the history of the Earth, a single species is reshaping the biosphere at a global scale. We are changing the composition of the atmosphere by burning fossil fuels, releasing carbon dioxide that has been locked in rock for hundreds of millions of years, and altering the climate of the entire planet. We are driving species to extinction at rates not seen since the asteroid impact that ended the age of the dinosaurs. We are transforming the land surface, the ocean chemistry, the nitrogen cycle, the phosphorus cycle. We are, in the geological sense, a planetary event. Now think about this from the perspective of the Fermi paradox. If our trajectory is typical, if most technological civilizations go through a phase of rapid industrial development followed by massive environmental disruption, then many civilizations might face the same kinds of challenges we face today. The collapse of ecosystems, the destabilization of climate, the disruption of the conditions that made complex life possible in the first place. How many of them successfully navigate that transition? How many find a way to develop the technology that comes after fossil fuels, the clean energy, the sustainable agriculture, the stable relationship with their biosphere, before the disruption becomes irreversible? How many tip over the edge into collapse? If most civilizations fail at this transition, then the great filter might be the Industrial Revolution. Not nuclear war, not artificial intelligence, just the fundamental difficulty of transitioning from a civilization powered by concentrated ancient solar energy to one powered by sustainable sources, before the accumulated damage becomes too great to survive. This is a sobering thought, because we are in the middle of that transition right now. We know the problem. We have the technology to solve it, or at least the beginning of the technology. We have the scientific understanding. What is uncertain is whether we have the collective will, the political capacity, the social coordination to make the transition fast enough. Whether we succeed or fail at that transition might have implications not just for us, but for the answer to the Fermi paradox. If we succeed, we become evidence against one version of the great filter. If we fail, we become a data point in support of it. This is not a comfortable thing to think about, but it is honest. The Fermi paradox is not just a question about what is out there. It is also a question about what is in here. About what we are doing with the extraordinary and fragile situation we find ourselves in. Let me try to give you a sense of the long view, not the human historical view, or even the geological view, but the truly cosmic view. Because the Fermi Paradox makes more sense when you understand how much time there is. The universe is 13.8 billion years old. That is its past, but the universe has an enormous future. The sun will continue burning for another 5 billion years before it expands into a red giant and eventually collapses into a white dwarf. Other stars will continue forming and burning for trillions of years. The lowest mass red dwarf stars, which are by far the most common type, can burn for 10 trillion years, hundreds of times the current age of the universe. The window for technological life in the universe is not closing. It is just beginning. The vast majority of the universe's habitable era lies in the future. If technological civilizations tend to arise during the middle years of a planet's habitability, as we did on Earth, then most technological civilizations have not yet arisen. They are still billions of years in the future. We are early, extraordinarily early. This has a remarkable implication. If we are early, if we are among the first technological civilizations to arise in the universe, then the silence is not paradoxical. It is expected. There is nobody to hear from because almost nobody has had enough time to arise yet. The universe is in its infancy, and we happen to be among the first minds to wake up in it. This is, in some ways, the most optimistic possible resolution to the Fermi Paradox. It does not require a great filter. It does not require civilizations to be rare or to destroy themselves. It simply requires that we are early, that the universe is just beginning its era of intelligence, and that the civilizations we might one day encounter or become aware of are not yet old enough to have made themselves known. If this is true, then we are not the culmination of cosmic history. We are its beginning, the first words of a very long story, and the silence that surrounds us is not the silence of absence or extinction or hiding. It is the silence of a universe that has not yet had time to fill with voices. That is a thought worth sitting with. We are early. The universe is full of futures. And the question that Fermi asked over lunch in 1950 might eventually answer itself, not because we find the answer, but because, given enough time, the answer finds us. We began with a simple question: where is everybody? And we have spent this entire journey circling it, approaching it from different angles, considering different answers, sitting with different implications. I do not have a final answer for you. Nobody does. The Fermi Paradox remains unresolved. The sky is still silent. The search continues. But I want to leave you with something, a way of holding the question that I find more useful than any of the proposed answers. The Fermi Paradox is ultimately a question about the relationship between intelligence and the cosmos, about whether mind is a cosmic phenomenon or a local accident, about whether the universe is, in some sense, friendly to the emergence of awareness, or whether awareness is a fragile, improbable flicker in an indifferent void. We do not know. But the fact that we are asking the question at all, the fact that we are capable of constructing the paradox and sitting with its implications, suggests something remarkable about the nature of intelligence. We are matter that has become capable of wondering about itself, of modeling the universe and asking why it is the way it is. That capacity, whatever its origin, is extraordinary, and it gives us a responsibility, not just to search, not just to listen, but to survive. Because if we are rare, if we are among the first or the few, then our existence is something the cosmos has very little of. Our minds, our curiosity, our capacity to ask where everybody is and to mean it seriously, these are things that may be extraordinarily scarce in the universe right now. That does not make us special in the sense of being important to any cosmic purpose. The universe has no purposes, it just is, but it makes us precious in the statistical sense, like the last specimen of an endangered species or the first flowering plant in a world that had never had flowers. Not cosmically significant, but genuinely rare, genuinely worth preserving. And so the Fermi Paradox, when you follow it to its deepest implication, becomes not just a question about what is out there. It becomes a question about us. About whether we will be careful enough, wise enough, cooperative enough to survive the dangers that come with power. About whether we will navigate the transition from a young, fractious, self-threatening species to something more stable and more durable. About whether the story of intelligence on Earth will be a short story or a very long one. The stars are listening, or they are not. We do not know, but we are listening, we are searching, we are asking. And the asking, the genuine, humble, curious, persistent asking of where everybody is, might be one of the most important things we do. Good night, sleep well, and look up sometimes. The universe is very large and very old and very quiet, and we are here awake, wondering. That is not nothing, that is everything. The formal search for extraterrestrial intelligence began in 1960, when a young astronomer named Frank Drake pointed the 85-foot radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, at two nearby sun-like stars, Tau Ceti and Epsilon Eridani. He called the project Ozma, after the Queen of the Land of Oz, a place very far away and very hard to reach. For 2 months he listened. He heard nothing from either star that could not be explained by terrestrial interference or natural astrophysical processes. Project Ozma was the beginning of a tradition. In the 60-plus years since, dozens of SETI searches have been conducted, using increasingly powerful instruments, scanning increasingly large regions of sky, listening across increasingly wide frequency ranges. The scale of the search has grown enormously. The early searches listened to a handful of stars. Modern searches can scan millions of stars. The early searches monitored narrow frequency bands. Modern searches monitor billions of channels simultaneously. And throughout all of that, the result has been the same. Nothing confirmed. Nothing that could not be explained as a natural phenomenon or terrestrial interference. Nothing that persisted, repeated, and demanded an extraterrestrial explanation. The timeline of the search is a strange one. In 1961, Drake gathered a small group of astronomers in Green Bank to think through the question of extraterrestrial intelligence. He wrote his equation on a blackboard, and they estimated the number of communicating civilizations in the galaxy. The estimates ranged from 1, meaning just us, to 100 million. The uncertainty was, and remains, enormous. In 1974, Drake and Carl Sagan composed the Arecibo message, a brief binary-encoded transmission sent from the Arecibo radio telescope in Puerto Rico toward the globular cluster M13, about 25,000 light-years away. The message encoded information about humanity, our biochemistry, our solar system, and the telescope itself. It was a symbolic gesture more than a serious attempt at communication. Any response would take 50,000 years to arrive, but it was our first deliberate broadcast to the stars, and it captured the imagination of the world. In 1977, the WOW signal was detected. In 1984, the SETI Institute was founded, providing an organizational home for the search. In 1995, Project Phoenix began, a systematic search of about 1,000 nearby sun-like stars using the world's largest radio telescopes. It ran for a decade and found nothing. In 1999, SETI at Home was launched, a distributed computing project that allowed millions of volunteers to donate their computers' idle processing time to analyze radio telescope data. At its peak, it was the largest distributed computing project in history, involving millions of participants worldwide. It ran for 20 years and found nothing confirmed. The Allen Telescope Array, funded in part by Microsoft co-founder Paul Allen, began operations in 2007. It was designed specifically for SETI, allowing simultaneous observations across wide frequency ranges. Funding difficulties and technical challenges limited its operation, but it expanded the search in important ways. In recent years, Breakthrough Listen, funded by the technology investor Yuri Milner, has brought new resources to SETI. Launched in 2016 with $100 million in funding over 10 years, it is the most comprehensive and well-funded SETI program in history. It uses major radio telescopes around the world, including the Green Bank Telescope and the Parkes Telescope in Australia, to survey the million nearest stars to Earth, the 100 nearest galaxies, and the entire plane of the Milky Way across a broad range of frequencies. Breakthrough Listen has not found anything confirmed, but it has dramatically increased the sensitivity and scope of the search, and it has produced some interesting observations. In 2015, it detected 15 fast radio bursts from the direction of a repeating source called FRB 121102. Fast radio bursts are among the most energetic phenomena in the universe, releasing more energy in a millisecond than the sun emits in days. Their origin is debated. Most astronomers think they are natural astrophysical events, perhaps associated with magnetars, extraordinarily magnetized neutron stars. But for a brief moment, the possibility that some of them might be artificial was taken seriously. It was not. The current consensus is that fast radio bursts are natural, but the episode illustrated the kind of careful, open-minded scrutiny that good SETI science requires. You cannot afford to dismiss anything without examination. The history of SETI is a history of expanding search and persistent silence. Each new instrument, each new technique, each new sensitivity improvement has allowed us to rule out more possibilities, to narrow the parameter space within which extraterrestrial civilizations might exist without our detection. And each year that passes without confirmation adds, in a small way, to the weight of the silence. But it is important to put the search in perspective. Even with 60 years of searching, even with Breakthrough Listen and the Square Kilometer Array, we have examined a tiny fraction of the possible search space. The number of stars, the number of frequencies, the number of possible signal types, the number of possible arrival directions, the number of possible timing patterns, the search space is almost incomprehensibly large. We have searched a small corner of an enormous room and found nothing in that corner. We have not searched the rest of the room. The silence is real, but it is not yet conclusive. There is a development underway that may transform the search for extraterrestrial intelligence in ways that are difficult to fully anticipate. It is the development of artificial intelligence capable of analyzing vast datasets in search of anomalies, patterns, and signals that might escape human attention. Traditional SETI analysis involves looking for specific types of signals in the data. narrowband radio emissions at specific frequencies. The kind of signal that a radio transmitter would produce. These searches are powerful but limited by our assumptions about what an artificial signal would look like. Modern machine learning techniques can do something different. They can search for anomalies without a prior expectation of what form the anomaly will take. They can scan through enormous datasets and flag anything that looks statistically unusual, anything that deviates from the expected background. This allows for a much broader, more assumption-free kind of search. Breakthrough Listen has been using machine learning to analyze its radio telescope data. In 2020, researchers applied a machine learning classifier to data from the Parkes telescope observing Proxima Centauri, our nearest stellar neighbor. The classifier identified a narrowband signal at 982, 2 MHz that met several criteria for an extraterrestrial signal. It appeared only when the telescope was pointed at Proxima Centauri. It did not match any known human-made interference. It drifted in frequency in a way consistent with the Doppler shift expected from a source on a planet orbiting a star. The signal caused significant excitement within the team. For months, researchers analyzed it carefully, and ultimately they concluded it was most likely a form of radio frequency interference from human technology. Its characteristics, while unusual, could be explained by Earth-based sources. It was not confirmed as extraterrestrial, but the process was instructive. Machine learning identified something anomalous that had been in the data for years without being noticed. Even though this particular signal was almost certainly not extraterrestrial, the technique demonstrated its power. It shows that there might be signals hidden in existing data sets that we have not yet found because we did not have the tools to look for them. As artificial intelligence becomes more powerful, as our ability to analyze enormous data sets improves, the sensitivity of the search will increase dramatically. We may be able to detect types of signals that our current techniques are blind to. We may find anomalies in astronomical data that were recorded decades ago, but never properly analyzed. The search is not just about building bigger telescopes. It is also about finding smarter ways to look at the data we already have. We stand at a particular moment in the history of the search. The tools are improving. The data sets are growing. The scientific community is, if anything, more engaged with the question of extraterrestrial intelligence than it has been at any point in the past. The Fermi Paradox is no longer a marginally respectable topic for a physicist to think about. It is a central question in astrobiology, in astronomy, in philosophy of science. In the next decade, several developments could significantly change the terms of the search. The James Webb Space Telescope has already demonstrated the ability to analyze the atmospheric composition of exoplanets in unprecedented detail. It has detected carbon dioxide in the atmosphere of an exoplanet. Future observations may detect other atmospheric molecules, including ones that could be biosignatures. Finding oxygen, methane, or other gases whose presence in an atmosphere cannot be explained without biology would be a profound discovery. Not intelligence, not civilization, but life. The upcoming generation of extremely large ground-based telescopes, the extremely large telescope being built in Chile, the Giant Magellan Telescope, the 30-meter telescope planned for Hawaii, will have far greater light-collecting power than existing instruments. They will be able to directly image planets around nearby stars, and potentially characterize their atmospheres. Finding a biosignature in the atmosphere of a planet orbiting a nearby star would not just change the terms of the Fermi Paradox. It would be one of the greatest discoveries in the history of science. The Square Kilometre Array, when completed, will be the most sensitive radio telescope ever built. It will transform our ability to search for radio signals from artificial sources. Even if it detects nothing artificial, its observations will constrain the parameter space of possible civilizations more tightly than anything before it. Future space-based gravitational wave observatories like LISA will open a new window on the cosmos, detecting signals from processes we currently cannot observe. Whether anything artificial might produce gravitational waves is speculative, but the new window itself could reveal unexpected phenomena, and the development of artificial intelligence continues. The ability to analyze complex datasets, to identify anomalies, to search without assumptions, to process information at speeds and scales impossible for human researchers, will increasingly be applied to the question of extraterrestrial intelligence. We may not know yet what that will find, but the tools are becoming more powerful. The question is still open. The search is still ongoing, and the silence for now persists. But silence is not the same as absence. The universe is very large, and we have listened carefully for only a very short time. Where is everybody? We are still asking, we are still listening, we are still looking, and that is the right thing to do. Sleep well. The question is out there under the same stars that have always been there, patient, waiting, unanswered. Good night. There is a thread in the Fermi Paradox literature that deserves direct and honest treatment. It is the possibility that the silence is primarily explained not by the rarity of life, not by the difficulty of intelligence, but by the near-universal catastrophic failure of technological civilizations at a specific point in their development, the point we are at now. This possibility has a name in the literature. It is sometimes called the sustainability solution to the Fermi paradox. The idea is that technological civilizations have a natural trajectory. They develop from simple organisms through complex life to intelligence. They develop language, agriculture, industry. They discover science and use it to gain enormous power over their environment. And then they face a crisis, a period in which the power they have accumulated grows faster than the wisdom and coordination required to manage it responsibly. Every civilization that reaches the technological level we are at must face some version of this crisis. The specific form will vary. For us, it takes the form of nuclear weapons capable of ending civilization in an afternoon, a changing climate that threatens the stability of the systems that support civilization, biological technologies that could be weaponized in ways that make nuclear weapons seem quaint, and artificial intelligence whose long-term implications we cannot fully predict. These are not small problems. They are existential problems. Problems where failure does not mean a setback or a crisis or even a regional catastrophe. Failure means the end of the civilization, the end of the experiment, the end of intelligence, at least on this planet, at least for this iteration. How many civilizations navigate this crisis successfully? We do not know. We have a sample size of one, and we are in the middle of it. We do not yet know whether we will succeed. But here is the thought that the Fermi paradox forces on us. If even 9 out of 10 civilizations fail at this point, if even 90% of technological civilizations destroy themselves when they reach our current level of development, then the silence is largely explained. 10 civilizations arise, 9 destroy themselves, 1 survives. The one that survives looks out at the sky and sees no signals, no megastructures, no evidence of anyone else. Not because the others never arose, but because they are gone. And the one that survives does not look special from the inside. It looks like every other civilization. It has the same problems, the same tensions, the same dangerous technologies. The fact that it survived is not because it was smarter or better or more virtuous. It is because it got lucky. Or because it found a way through that the others did not. Whether we will be among the civilizations that find a way through is something we genuinely do not know. The problems we face are real. The risks are real. The possibility of catastrophic failure is real. No honest account of our situation can pretend otherwise. But the fact that we are aware of the risks, that we can model them, that we can reason about them, gives us at least the possibility of doing something about them. A civilization that knows it faces existential risks is in a different position from one that does not. Awareness does not guarantee survival, but it is a necessary condition for it. The Fermi Paradox, in this light, is not just a scientific puzzle, it is a warning. A statistical argument that civilizations like us tend not to survive. An argument that should motivate us to think seriously about our situation and to act with the wisdom that the situation demands. We have the intelligence to understand the problem. The question is whether we have the wisdom to solve it. I want to end this journey not with uncertainty, but with possibility, because the Fermi Paradox, for all its unsettling implications, points towards something extraordinary about the moment we live in. We are the first generation of humans to know that planets are common. The first to know that the conditions for life might exist around billions of stars in our galaxy alone. The first to have built instruments sensitive enough to detect the signatures of distant worlds. The first to have sent spacecraft beyond the solar system, to have launched our own signal into the interstellar void, however faint. We live in the era when the search began. The era when humanity first developed the tools to ask the Fermi Paradox question empirically rather than just philosophically. The era when the answer, whatever it is, might begin to become knowable. That is an extraordinary thing to be part of, and we live in an era when the decisions we make collectively as a species will determine a great deal about what comes next. Whether we navigate the existential risks and build a civilization capable of persisting and growing for millions of years. Whether we develop the wisdom to match our power. Whether we find a way to cooperate globally in the face of threats that respect no borders. Whether we become the kind of civilization that other civilizations, if they exist, would be glad to share the galaxy with. These are not small things. They are the largest things. They are the questions on which everything else depends. The cosmos we will inherit, if we survive, is unimaginably rich. A galaxy containing hundreds of billions of stars, trillions of planets, billions of years of future history in which mind might grow and flourish and encounter whatever else is out there, or is not. A future in which the question of where everybody is might finally find its answer. We do not know what that answer is. We may not live to hear it. But we are the generation asking the question in the most serious and scientifically rigorous way in human history. We are the generation building the tools to search. We are the generation that, for the first time, has a real chance of finding something, or of becoming the evidence that something found us. Enrico Fermi asked where everybody was over lunch. He was eating a sandwich and talking with colleagues, and the question came to him almost as a joke. But the universe does not joke. The sky is vast and dark and mostly silent. We have been listening for 60 years, and we have heard almost nothing that demands an extraterrestrial explanation. The silence is real. Its meaning is not yet known. Maybe we are alone. Maybe we are early. Maybe we are hidden from something dangerous, or protected by something wise, or simply undetected by civilizations that have given up looking, or that look in ways we cannot perceive. Maybe the answer will come tomorrow, from a radio telescope in Australia, or a gravitational wave detector in Louisiana, or an optical telescope on a Chilean mountaintop, or a spacecraft approaching a distant star. Maybe the answer will come in a century, or a millennium, or never, but we are asking. And the asking is, in some profound sense, the most important thing we do. Where is everybody? We do not know, but we are listening. Good night. I want to return to scale one final time, because scale is the thing that makes the Fermi Paradox feel the way it does, not as an intellectual exercise, but as something almost physical. Something you can feel when you stand outside on a clear night and let your eyes adjust. The Milky Way is our home galaxy. It is a spiral galaxy, about 100,000 light-years across and about 1,000 light-years thick at our position, with a central bulge that is thicker. It contains somewhere between 200 and 400 billion stars. The Sun is one of them, a completely ordinary G-type star, roughly middle-aged, sitting about 26,000 light-years from the galactic center, in one of the spiral arms, in no particularly notable position. From Earth, on a clear night, far from city lights, you can see the Milky Way as a pale band of light stretching across the sky. That band is the disk of the galaxy seen from within. The individual stars are too far away and too numerous to resolve, but their collective light is visible. You are looking in that moment at the combined light of hundreds of billions of stars. And among those stars, almost certainly, are planets. Many of those planets are inhabitable zones. Some of those planets may have life. Some of that life may be intelligent. Some of that intelligence may have technology. Some of that technology may be capable of interstellar communication. And yet when you look at that pale band of light, you see nothing that says we are here. No signals strong enough to be obvious. No megastructures blocking starlight in clearly artificial patterns. No laser pulses. No nothing. Just the steady, ancient, indifferent light of stars. The Andromeda galaxy is 25 million light-years away. On a very dark night, it is visible to the naked eye as a faint smudge. It is the most distant object visible without a telescope from most locations on Earth. It contains roughly 1 trillion stars. In its hundreds of billions of years of history, the conditions for life have existed on countless planets within it. And yet from here it is a smudge, indistinguishable from any other diffuse object in the sky. The observable universe contains 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The total number of stars is somewhere around 10 to the power of 23. That is 100 million stars, and the universe is 13.8 billion years old, and planets are common, and the chemistry of life is universal, and the sky is quiet. That quietness held against those numbers is the Fermi Paradox in its most elemental form, not a calculation, not an equation, just the strange, vertiginous feeling of knowing how big the universe is and how old it is and how full it should be, and then looking up at the quiet stars. Where is everybody? It is the right question. It may be the most important question. and it remains, as of tonight, beautifully, frustratingly, magnificently unanswered. The universe does not owe us an explanation. It does not owe us company. It does not owe us anything. It simply is. Vast, old, dark, mostly silent. And here we are in it, small and temporary and inexplicably curious, pointing our instruments at the sky and listening. That is who we are. That is what we do. And whatever the answer turns out to be, the asking is worth it. Sleep well. The stars will still be there when you wake up. And somewhere among them, maybe, something is also awake, wondering the same thing. Good night. One of the most striking things about the Fermi Paradox is how it forces us to think in timescales that are utterly foreign to human intuition. We are a species that thinks in years, in decades, at most in centuries. The timescale of a human life is perhaps 80 years. The timescale of recorded history is perhaps 5,000 years. The timescale of our species is perhaps 300,000 years. All of this feels enormous from inside it. From inside a human life, 5,000 years of history is almost unimaginably long. But against the backdrop of the Fermi Paradox, 5,000 years is nothing, less than nothing. The universe is 13.8 billion years old. The history of our civilization occupies less than 1/1,000,000th of cosmic time. Our technological civilization, the kind that produces radio waves and rockets and particle accelerators, is perhaps 300 years old. 300 years out of 13. 8 billion. The ratio is so small it barely registers. Now consider what this means for civilizations older than ours. A civilization that arose on a planet orbiting a star that formed 5 billion years before our sun. They had a 5 billion year head start. If they followed a trajectory anything like ours, they would have been technological for billions of years. They would have had billions of years to develop, to change, to grow, to spread. What would that look like? What would a civilization with 1 billion years of technological development be capable of? We genuinely do not know. We can barely project our own trajectory 50 years forward with any confidence, let alone 1 billion. But some things seem at least plausible. A civilization with 1 billion years of development might have mastered energy production at scales we cannot currently imagine. The sun puts out an enormous amount of energy. A civilization capable of capturing even a fraction of a star's total output would have energy resources utterly beyond our current comprehension. With that energy, they could do things we cannot. Build structures of astronomical size, accelerate spacecraft to significant fractions of the speed of light, communicate across interstellar distances with signals powerful enough to be heard by any civilization with even modest receiving equipment. And yet, no such signals have been detected. No such structures have been observed, except for occasional anomalies that were ultimately explained by natural processes. The silence persists even when we look for the signatures of civilizations far more advanced than us. This deepens the paradox rather than resolving it. If advanced civilizations should be more visible, more powerful, more capable of making themselves known, then the absence of their signatures is more surprising, not less. The silence is not a reflection of our limited detection capabilities. It is a silence that, in principle, should have been broken by now, unless there are no advanced civilizations to break it, unless something prevents civilizations from reaching the timescales at which they would become truly visible. Unless the great filter is real and it is ahead of us, or unless advanced civilizations are there but invisible to us for reasons we do not understand, hiding, silent by choice, operating in ways that produce no signatures we can detect. Perhaps the absence of signatures is not absence of civilization, but evidence of a kind of civilization we cannot see. We do not know. We are left, as we always are, with the Fermi Paradox, sitting with an answer that is not yet an answer. A question that is not yet resolved. A silence that is not yet explained. That is the honest place to be. It is uncomfortable, but it is honest. And honesty about the universe and about our place in it is the foundation of everything worth knowing. Where is everybody? We are still listening. Good night. There is a final thought I want to leave you with. It is not a solution to the Fermi Paradox. It is not a new hypothesis or a calculation. It is more like a posture, a way of holding the question. The universe has been our teacher for as long as we have been capable of learning from it. Every time we have looked carefully at the cosmos, we have found that it is stranger and richer and more surprising than we expected. We thought the Earth was the center. It is not. We thought the sun was the center. It is not. We thought the Milky Way was the entirety of the universe. It is one of 2 trillion galaxies. We thought space was static. It is expanding, and the expansion is accelerating. We thought atoms were solid. They are mostly empty. We thought time was absolute. It is relative. We thought light was instantaneous. It is not. At every turn, every time we brought our instruments to bear on the question of what the universe is, we found that our intuitions were wrong in ways we could not have anticipated. The Fermi Paradox might be another lesson in the same tradition. It might be the universe teaching us that our intuitions about intelligence, about civilizations, about what the cosmos should look like if it contains minds, are wrong in ways we cannot yet anticipate. Maybe civilizations do not expand the way we expect. Maybe intelligence does not communicate the way we expect. Maybe the signatures of advanced life are not the kind of things we are looking for. Maybe the universe is full of mind and we are blind to it, the way a fish is blind to the water it swims in. Or maybe the universe is teaching us something darker. Maybe the silence is a lesson about the rarity of persistence, about how hard it is to build something that lasts, about the fragility of intelligence in a universe that does not particularly care about its survival. Either way, the universe is teaching us something, and we would be wise to listen. We have been asking where everybody is for at least 70 years in a rigorous scientific sense, and for millennia in a mythological and religious sense. The question is as old as the human capacity to look up and wonder, and it remains open. But we are better equipped to answer it now than we have ever been. We have instruments of extraordinary sensitivity. We have theoretical frameworks of great sophistication. We have a community of scientists across disciplines and across the world who take the question seriously and pursue it rigorously. We have computing power that would have seemed miraculous to the scientists of previous generations. We have space telescopes and gravitational wave detectors and radio arrays and optical interferometers and a whole ecosystem of tools pointed at the sky and listening. We are ready in a way that no previous generation of humans has been ready to receive an answer if one is out there to be received. That is something extraordinary. That this species, which emerged on a small planet orbiting an ordinary star in an unremarkable galaxy, has developed the capacity to ask one of the deepest questions the universe can pose and to actually search for the answer rigorously, empirically, persistently. That is not nothing. That is, in fact, remarkable. Where is everybody? We do not know, but we are asking with everything we have, and sometimes that is enough. Sleep well tonight. The universe is very large and very old, and it keeps its secrets carefully. But we are learning. Slowly, imperfectly, persistently, we are learning. That is what we do. Good night.